Okay, so for this problem, we have a biased coin that is heads with probability p. So we can assume it's tails with probability 1 minus p. And we're going to flip this coin n times. And so we define a run as a sequence of consecutive heads or consecutive tails. And we want to know the expected number of runs. So first, to make sure we understand the question, if I had a sequence heads, heads, tails, 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 heads, there are 3 runs because I have these 3 sequences of consecutive heads or tails. So the first clue when solving a problem like this is we see that it's asking for an expected number, which is great because then that suggests we should use linearity of expectation. But first, we need to pick a random variable. And so what are we actually trying to find? We're trying to find the number of runs. So we want a random variable that will count the runs. In other words, we can make an indicator random variable xi, which is 1 if a new run starts at flip I and 0 otherwise. So we have to be a little careful because this is a good definition. This is truly a random variable as long as I is at least 1 and at most n. But x1 is always 1 because the first flip will always start a new run. So if we want to count the number of runs, or the expected number of runs, if we do it n flips, what we need is this expectation. Expectation of x1 plus x2 plus xn. So now we use the most powerful thing we have available to us, which is linearity of expectation. Which says that we can write this expectation of a sum as a sum of expectations. And since x1 is a little different, I'll keep it separate from the others. And then we get the following. Okay. And then we note that this is just 1 plus n minus 1 times the expectation of xi, because the expectations of xi are all the same. So now, how do we compute the expectation of xi? Well, if we're at the ith flip in some sequence of heads or tails, in order to know if it's going to start a new run, we need to know what the previous flip was. And so this suggests to calculate this, we should just brute force the possibilities, or in other words, use conditional expectation. So we can condition on whether the I minus 1 flip is heads times the probability the I minus 1 flip is heads plus the expectation of xi given the I minus 1 flip is tails times the probability that the I minus 1 flip is tails. So I always like to do the probabilities first because those are easy. Since this coin, its result is independent, so the probability that I minus 1 flip is heads is p. So this is the expectation of xi if the I minus 1 is heads times p, plus the expectation of xi if the I minus 1th is tails. And then the probability that the I minus 1th flip is tails is 1 minus p. And then we're almost done. All we need to do now is compute this expectation. Okay. So if the I minus 1 flip is heads, then the expectation, we start a new run on the I flip if and only if the I flip is tails. So this is 1 times the probability it's tails plus 0 times the probability it's heads. Because remember, if it doesn't start a new run, then our expectation is 0. So we can actually just ignore this, but I write it for completion. And then similarly, this term, if the I minus 1 flip is tails, we only start a new run if the I flip is heads. So this is 1 times the probability the I flip is heads, which is p. So together, the expectation of xi is 1 minus p times p plus p times 1 minus p. And so then by linearity of expectation, the expected number of runs is 1 plus, so I'm using this, what we solved for here. So it's 1 plus 2 times n minus 1 times p times 1 minus p. And that is our expected number of runs.